Hi everyone, my name is Ivan Grolikov. I'm VP of Software Platforms at Espressif. My talk today is about ESP-IDF build system. Last year, in the talk about developing and publishing ESP-IDF components, I have already touched upon some of the topics related to the build system. This year, I want to focus more on the project structure, the configuration process of ESP-IDF projects, and an important topic about the component requirements. I will also give you practical suggestions on how to solve common tasks with the ESP-IDF build system. Let's begin. Here is the plan of today's talk. The first part is the introduction. I will tell about the terminology and some of the basics of the build system. Then the main part, it's a walkthrough. We will create an ESP-IDF application and pay attention to the build system related topics. I will explain how certain things work in the build system. And the final part is a set of recipes that you can apply to your projects. The slides of this talk are available online over at this link. You can also scan the QR code to get there. I have many links in the slides, so if you're following along, I suggest opening the slides so you can click on the links. Let's go to part one. And first I want to tell what I want to achieve with this talk. When we talk to customers, we hear some of the common questions. Some of them are related to the build system. And typically, those are the questions about structuring the projects, using the build system correctly and effectively, getting the most out of it. I hope that by the end of the talk, if you have already used the ESP-IDF build system, some of those things will become more clear to you. If you haven't used the ESP-IDF build system yet, then I hope this talk gives you enough information to get started comfortably. Here are some basics about the build system. The IDF build system compiles applications which consists of components. Component is the name of library in an ESP-IDF application. Components can be either part of ESP-IDF itself, they can be part of the application project, so developed by application developers, and also come from different other sources, from third parties. Aside from compiling the code, ESP-IDF build system also configures the program based using a system which is based on kconfig. I will explain this compile time configuration flow in a bit. ESP-IDF build system also generates IDF specific artifacts such as partition tables, linker scripts, bootloader, and so on. And there is integration with interactive tools such as tools for configuration, let's say menu config, flashing tools, serial monitor, debugging, and emulation tools. And finally, IDF build system is able to download components from ESP component registry, giving you access to hundreds of components developed by Espressif and third parties, and eventually saving you time when developing your project. How do different parts of ESP-IDF build system relate to each other? The build system itself is written in CMake, and when you run the build process, you typically invoke either the command line interface IDF-PY or one of the IDE extensions. Those extensions they call CMake, and CMake in turn executes the CMake list file inside the application, and that in turn executes the CMake list files inside ESP-IDF. Finally, CMake, based on all those CMake list files, generates the build script, and the build script is executed by another tool, typically by Ninja or by GNU Make. During this process, at various steps, the build system will call the cross compiler or some of the IDF specific tools. This happens quite in the background. What we will focus on today is the part of the build system that is implemented in your project. So the CMake list files that you write in the application project, we will not talk much about what happens inside the CMake list files inside ESP-IDF, so the underlying implementation. Also, before we start the main part of the talk, I want to talk a bit about why we have this talk specifically about IDF build system rather than just about modern CMake. To explain this, I have to go a bit back to the time when ESP-IDF didn't use CMake build system, and Up until version 4, IDF was using a build system based on GNU Make. Here are what the make files written for GNU Make look like. You see that there is very little boilerplate, which means that for the make files to be that simple, there has to be a lot of implicit behavior. And when we were developing a CMake-based build system for IDF 4.x, we took a lot of that style from the GNU Make build system to ease the transition from GNU Make to CMake for existing users. Therefore, the CMake-based build system that we introduced, it also contains a lot of implicit behavior, which is intended to simplify the make files that we write as much as possible. Internally, the IDF build system does use modern CMake concepts, such as declaring libraries, declaring private and public properties of libraries, and using target link libraries as a glue between them. However, there are important differences with regards to how libraries are added to the build, and as a result, a plain CMake library typically cannot be used as an IDF component. And we need to wrap that CMake library into an IDF component in order for it to be used. There are some links to GitHub issues with discussions about incompatibilities between ESP-IDF build system and plain CMake that I'm going to leave here. And before we move on, I just want to say that we do recognize this as a problem, and in the future versions, IDF will move closer to plain CMake so that people who know how to write CMake-based projects will be very comfortable in ESP-IDF build system. Let's move on to part 2. Here we talk about building an application using the IDF build system. We start off with creating a project, and for that we can use the idf-py create project command. If you're using an IDE, then there is going to be usually a way to create a project from a template. And when you create a project, either using this command or using the IDE template, you will get something like this. Typically, there is a CMake list file in the project directory, and then there is the main subdirectory with the source file and another CMake list file. At the root of the project, there is a project CMake list file, and the very basic version of it only defines the project and gives the name. In this case, the name is just the app. Then there is another CMake list file, which is inside the main subdirectory. Now, the main subdirectory is a component. You can have more components in the application than main. This is just the default location where you often start putting your code. The main component CMake list file also looks pretty simple, and it only declares, in this case, the only source file that the application consists of. And in the template, the source file just has an empty app main function, which is the entry point of the application. Now we can build the project. When you run idf-py build, as I mentioned before, it will execute CMake. The CMake will generate the build script, and the build script is now being executed by a tool called Ninja. Finally, at the end of the process, we will get the compiled application in the build directory. So the build process is complete. We can take a look at the result. We see that 2 new files have been created. There is an SDK config file and there is a build directory. And inside the build directory, there are many files, but the important ones I listed here. There is a config subdirectory with the sdk-config.h. If you have already written the application, you will know that the sdk-config.h is where this C code can take compile time configurations from. There is a bootloader directory, the partition table, all those things get flashed onto the chip along with the application. The application binary that gets flashed, the application elf file that can be used for various tools such as debugging, GDB step, core dump, and so on. The map file can be used to analyze the application size layout using some IDF commands like idf.pysize. Compile commands JSON is the so-called compilation database, and it often is used by IDEs to provide code navigation and automatic completion. Project description JSON contains project metadata. It's an ESP-IDF specific file, and it's a way for the build system to communicate information about the project to various command line tools and to IDEs. And finally, the two Flasher related files, they contain all the information needed to flash the project and are used by tools such as idf.pyflash. In addition to the build directory, there is also SDK config file, which stores compile time configuration of the project. The SDK config file can be modified either manually or using GUI tools or using command line interface such as menu config. And we can either consider it as a build artifact, so add it to git ignore, or we can track it in Git. I will explain the difference between those two approaches in a moment. Before we move on to talking more about extending our project and adding more features to the project, let's talk about the configuration system. The configuration system is designed to create the two files sdkconfig.h and sdkconfig.cmake, which provide a set of compile time configuration options which can be used in C code for sdkconfig.h and in CMake for sdkconfig.cmake. The source of the configuration is the file called sdkconfig, and at first when we compile the application until sdkconfig is created, the configuration system reads all the information about the configuration options from kconfig files. It gets the default values from sdkconfig.defaults file if it exists, or if it doesn't, from kconfig files, and generates the initial version of sdkconfig, and also generates the initial version of sdkconfig.h and sdkconfig.cmake. After you edit the sdkconfig file, either manually or using a tool such as menu config or a GUI configuration editor within the IDE, the sdkconfig file will be modified. And after the sdkconfig file is modified, there is a configuration regeneration process. So the output files will be regenerated based on the information in sdkconfig, so updated configuration, and again values in kconfig files and in sdkconfig defaults, in case some value is missing from sdkconfig. Finally, the new sdkconfig.h and sdkconfig.cmake files will be created and used throughout the build process. You can also take the sdkconfig file and create sdkconfig defaults based on sdkconfig. This means that all the settings that are equal to their default values that are specified in kconfig files will not be included, but any setting that you have changed, that you set differently from the default value in kconfig file, will be added to sdkconfig.defaults. If you use this approach, then you can put sdkconfig.defaults file into your Git repository, and you can add sdkconfig to git ignore, and you can then use this sdkconfig.defaults file as the main source of truth for the configuration of your project. So to summarize, all components in the application can define compile time configuration options using kconfig files. The sdkconfig file will be created based on the defaults in sdkconfig.defaults and in kconfig files. The sdkconfig.h and sdkconfig.cmake will be generated based on sdkconfig. And you have a choice of either tracking sdkconfig or sdkconfig.defaults in Git, and you can choose between the two options based on what you prefer. Keeping sdkconfig in Git gives you more stability in the sense that updating the ESP-IDF version is guaranteed not to change the options automatically, but the other approach is to keep sdkconfig.defaults in Git, and that has the advantage that you actually will receive the updated values in case ESP-IDF gets updated, and also sdkconfig.defaults file is much easier to document and explain why you want a specific value of a given option. So it might be better for maintainability. Now, this was the brief introduction to the configuration system. Let's move back to our project, and it's time to take a look at the component CMake-list file. Inside the component CMake-list file, we see the IDF component register function, which in our example only added one source file and one include directory. The main things that you will be doing with the IDF component registry is IDF component register function is defining the list of source files, either using the srcs keyword or list of source directories using src-dirs keyword. You can define the list of include directories using include-dirs or priv-include-dirs keywords, and you can define dependency between components, and we will talk about the dependencies topic in a bit. There are also some additional parameters you can specify to IDF component register, such as for linker fragments, embedding files, and so on. I will not cover this in detail. This is covered in the documentation. In addition to using IDF component register inside your component CMake list file, you can use other common CMake functions. For example, if you want to work with lists, you want to work with files, or you want to generate something before compiling it, then you can implement those steps as you would in normal CMake. The common thing that you will be doing after creating the application is probably creating new source files and new header files. And in this case, in our template application, I have added a new source file appcommon.c. I have also moved both source files into the src directory, and have created an include directory where I have added a file appcommon.h. And after those changes, the component CMake list becomes like this. So the srcs now contains two sources, and the include directory, this is a private include directory. Again, I will explain the distinction between the two. The include directory is include. A few tips. First of all, if you have a choice, I would recommend using sources keyword rather than source dirs. Basically, it means that you list all the files explicitly. This gives you much more predictable behavior, and in case you add a source file but you forget to commit it into the project, then you will get the error, which will be much more obvious than if you just used src-dirs. Another tip is to never use paths that point outside of the component. For example, include paths that point somewhere to another component's include directory. This is pretty much always an incorrect thing to do, and if you find yourself doing this, then it means that something is wrong with setting the component requirements, and I will explain how to set the requirements correctly in a second. You can use double quotes, or you can skip your double quotes. The only case when you need double quotes is if the path to this source file or the name of the source file contains a space. Otherwise, double quotes are not necessary. I'm using them here in the example just because it makes better syntax highlighting. The next thing that you can do after adding your own source files is adding dependencies to external components. And this is done using a file called idfcomponent.yaml. It is a IDF component manager manifest file. The components are added to this file in the dependencies dictionary. I will not cover the syntax of this file too much in detail. Here is a link for the documentation of IDF component YAML. But in the most simple case, you just list the components that you want to add to your application and the versions of those components. When the build system runs, those components will be downloaded into a new directory called Managed Components. Managed Components is also a generated directory, so it's recommended to add it to gitignore and not modify the directory. The components will be downloaded inside this directory and added to the build. Additionally, there is going to be a file called dependencies.log, which will contain actual versions of all the dependencies, meaning that if you want to achieve reproducible builds, then it's recommended to keep this file around. You can also achieve reproducible builds by specifying exact versions of dependencies in the manifest file, but the log file gives you a better guarantee. Now let's return to the topic of configuration and see how we can add configuration options to our component. As we talked before, configuration options are defined in kconfig files or kconfig projbuild files. The difference is only where those configuration options appear in the configuration editor. If you add an option to kconfig file, it will appear under the component config part, and if you add the option to kconfig proj build, then it will appear in the root menu of the configuration editor. Kconfig files have the same syntax as kconfig in other systems like Linux or Zephyr. I left a link to kconfig syntax reference here. And in kconfig file you can define options of different types, for example Boolean options or string options. The recommendation is to define things in kconfig that really need to be known at compile time, and avoid defining things that are more of factory settings or things that might change at runtime. For those things, it's better to have a runtime variable, for example, that can be set during the application execution, or if it is a factory setting, then you can store it inside NVS or some other file system. However, kconfig options can also be convenient for some simple configuration or setting some default values, so you can use them for those purposes as well. Now let's talk about what happens when the application has been developed for some time and it has now more and more functionality. So you might find having a lot of source files in your main component. This might be the point when you could consider splitting the main component and introducing additional components in your application. The reasons why you could split the main component and introduce additional components could be to simplify maintenance. For example, if you have more than one developer on your team, maybe different developers will be responsible for different components. The second reason could be to reuse those components between products. If you have multiple applications or you're building applications for multiple products, you may have some common parts of functionality that you will not keep in each single project. And in this case, moving this functionality into a separate component can let you reuse the code. And finally, sometimes creating separate components for different parts of your code forces you to think about responsibility of each source file, each header file, and create stronger and more clear interfaces between parts of the code. And that also helps with maintainability and avoids having really complex dependencies in your application. How to create a new component? We do this by creating a directory called components inside the application and adding a subdirectory there. The name of the subdirectory is going to be the name of your component. In this case, I've added the app-common subdirectory into the components directory of the application and moved the two files that I have created prior to this, app-common and .h and app-common.c. Now app-common is a component and it can be reused between different applications if I have some common functionality for all my apps. The structure of the component defined in components directory is the same as for the main component. You can have a CMake list file, you can have IDF component YAML file, you can have kconfig and all the other things that we talked about, and also the things we will cover in the future. What's inside the new component? So we have CMake list file. Again, in this case, it only adds one source file and one include directory. So it's the same as we've seen before. I've added a sample piece of code both to the header file and the source file. It's just a simple function that initializes storage from application perspective. And in practice, this function to initialize the storage just calls the NVS flash library to initialize it. Now, if we put this all into our existing sample application and try to build it, then we will actually run into the following compilation error that the nvs.h file hasn't been found, and we used nvs.h, nvs-flash.h over here. You might wonder why that is the case, because if we put the same exact code into the main component like we had previously, then everything will compile successfully. If you are using a recent version of ESP-IDF, you will receive additionally a hint after this error message, and the hint is going to tell you that the compilation failed because the source file in your app-common component included nvs-flash.h, but it didn't add nvs-flash.h into the requirements list, and the solution would be to add nvs-flash to prev requires list when you're calling IDF component register in the CMake list file of app common component. If we follow this hint and we modify the CMake list file of the component like this, basically just adding nvs flash after the priv requires keyword, then the build will succeed. This brings us to the topic of requirements, why they are needed and what they actually do for the build system. The priv requires list that we pass to IDF component register, this one, is a set of components that we can use in the source files of our current component. If you're familiar with CMake, then it is equivalent to calling target link libraries, where the first ellipsis is your library and the second ellipsis is the target library, basically the library from which you want to use the header files or the functions. Additionally, there is also a requires list, and it's different in that if you need to use a header file of another component in the public header file of your own component, then instead of priv requires, you have to add that dependency into the requires list. And what this does, in addition to what priv requires does, is it propagates the dependency on the target component also to the components that use your own component. So it becomes a transitive dependency. So here is a summary. You use priv requires same way as you would use CMake keyword private, and the dependency is added, in this case, only to the sources of your component. If you use this IDF component register keyword requires, then it's equivalent to using CMake keyword public, and in this case the dependency is added not only to the sources of your component but also to the dependent components. Here is an example that is related to our previous situation, where we had the main component with main.c, app common component with appcommon.h and appcommon.c, and two other components, ESP-common and nvs flash. The requirement that we were missing was this one, number one, and appcommon.c uses a function defined in nvs-flash.h inside nvs-flash component, and therefore appcommon.c needs to have nvs-flash in its priv requires list. The second requirement from main.c to appcommon.h, so if main.c calls the function defined in appcommon.h, it's very similar, because main.c calls a function defined in appcommon.h. The CMake list file of the main component needs to have priv requires appcommon to declare this dependency. There is actually a third dependency in here that we haven't talked about before, because appcommon.h is a public header file of appcommon component, meaning that it can be used by other components, like main in this case. Because appcommon.h uses another header file, esp-error.h from ESP-common, appcommon would need to have ESP-common on its public requirements list. However, as you noticed, in practice we didn't have to add this, and I will explain why in a second. So first, there are two things to note. When we had the appcommon header file and appcommon source file inside the main component, we actually didn't need to add the requirement at all, and the compilation succeeded. Why is that? Well, the main component is special in ESP-IDF build system, and this is the behavior that has been carried over from the previous GNU Make build system. In GNU Make, there was no concept of requirements between components, so every component in the build could use every other component in the build. However, when we migrated to CMake, we wanted to introduce those requirements, but to simplify migration, we kept the behavior that the code in main component can still use header files from every other component in the build. And this works until you start specifying dependencies for the main component. So, if the main component doesn't specify any dependencies, then implicitly it is made dependent on all the components in the build. As soon as you add requires or priv requires to your main component, then you have to start specifying all the dependencies. Now, I don't recommend relying on this behavior. It's convenient when just combining features from different examples really quickly without having to worry about dependencies. But if you're developing a real application, I would recommend thinking about the dependencies, which components you use, and adding those components to the requirement list. You can read more about this in this documentation link. The second caveat here is related to the reason why we don't actually have to add ESP common to the requires list of app common. And this is related to common requirements. There are certain components that, for reasons of backward compatibility and also for convenience, are automatically added as dependencies to every other component in the build. It means that if you're using a header file, for example, from heap component or log component or ESP common component, like in the previous case, then you don't have to declare that dependency, and IDF build system will automatically add that dependency to every component. This list of common requirements will most likely shrink in the future. Primarily, this should happen in major releases of ESP-IDF. So in ESP-IDF 6.0, it is likely that a few components will be removed from the list of common requirements, and you will have to declare dependencies on them explicitly. So those two caveats explain why first of all, why we didn't have to declare dependencies when app common files have been in the main component, and second, why we don't have to declare dependency on ESP common from app common. There are a couple of things that I also want to point out with regards to limitations associated with the requirement system. And the first one is that requirements between components cannot depend on kconfig options. For example, this snippet will not work. You might expect that we can check if a certain configuration option is set, and we can add the component dependency into the requirements list, but this will actually not work. And what will work is adding the dependency late. So for example, we can call IDF component register without specifying that additional dependency, in this case on ESP-PS-RAM, but after IDF component register, we can call an CMake-if command to check if that configuration option is set, and if it is set, then we can add the requirement on ESP-PS-RAM later. And the reason for this is the process of CMake list file evaluation in ESP-IDF, where actually every component CMake list file is evaluated twice. The first time every CMake list file is evaluated to find the dependencies between components, to scan for requirements, and the second time it is actually added to the build using CMake add subdirectory command. For that reason, you cannot call any CMake commands which don't work in script mode until you call IDF component register. So after IDF component register, all CMake commands, including those that only work in project mode, not only script mode, will work, but IDF component register has to be relatively early in your component CMake list file. Now, this is one of the limitations that I mentioned before when talking about compatibility between plain CMake libraries and IDF components. So this is something that you need to keep in mind, especially if you are porting an existing CMake library into ESP-IDF. Sometimes you will have to wrap that CMake library into an IDF component to resolve this problem. What do component requirements actually give us? The main thing is that component requirements allow us to compile only what is actually needed in your application. If you remember, when I built the sample project, it compiled nearly 800 files. And this is because all the source files in ESP-IDF have been compiled. And the reason for this is because the implicit behavior of main component, where it depends on everything by default. As soon as we start specifying requirements, meaning that we specify the requires and prerequires in component CMake list files, and we also set the components variable in the project to some smaller set of components, we can trim the build, meaning that we can only add the components that are in the components variable, plus all the components that those components depend on. There are some docs that explain this further. I left a link here. Here's what it's going to look like in practice. In our project, we will add set components main before calling the project function, and then in the CMake list file, in this case the main CMake list file, we also specify the requirement on app common. Now, if we build the project after this, then the build will take much less time, and also fewer components will be built. There is another caveat here to keep in mind, that certain features require the respective components to be included in the build. And if you follow this approach, then you might not actually have those components in the build by default. For example, if you want to have PSRAM support, you need to make sure that ESP-PSRAM component is included. If you want to use GDB stub, you need to make sure that ESP-GDB stub is included. If you want to use core dump, you need to make sure that ESP core dump is included. And you can include them either by adding them to this list of components, or by adding them as a dependency into one of the CMake list file of your components. Now that concludes the second part of the presentation. We have walked through the main things that you need to know when creating the application, and now I will give you a set of recipes for different things that you might want to do within the build system. One of the common things you may want to do is to do things conditionally in the build system. For example, conditionally add files, meaning that you check if a certain configuration option is set and you only compile a certain file if that is true. The syntax is pretty simple. As I mentioned before, we cannot use commands that cannot be used in CMake script mode until we call IDF component register. But all the basic commands such as set, if, list, and so on, they can be used in script mode. So we can perform some logic based on configuration options and create a list of source files and then pass them to IDF component register. Another approach might be more familiar to CMake developers who have already used target sources command. In this case, we register the component providing only the common source files, and then depending on whether a certain configuration option is set, we're going to call target sources to add additional source file to the component. In IDF component CMake list file, this component lib is a predefined variable that contains the name of the library target of the current component, and you can use this variable wherever you're calling CMake target functions. For example, target sources, target include directories, target link libraries. Another common task is to add compiler flags or compile definitions. If we want to add compile flags, we have to decide for what set of source files we want to add that flag. If we want to add compiler flag for the whole component, we can use target compile options CMake command, and in this case we again specify component lib as the target and the flag that we want to add. If we use private, then the flag will only be added to the source files of the current component. If you use public, then the flag will be also added to this when compiling the source files of all the components which depend on this current component. You can check the CMake documentation reference about the target commands, not only include the ones about target compile options. If we want to apply the flags to a specific source file, and this is commonly done if we have, let's say, some upstream sources that have some compilation warnings, we want to exclude those warnings from the build, then this can be done using set source files properties command. And in this case, we use the compile options property and specify the flags that we want to add. Sometimes it is necessary to set the flags for the whole project, like for instance in the case when we want to enable undefined behavior sanitizer. If we want to enable a certain compilation flag for the entire project, then there is a IDF specific command called IDF build set property, and the name of the property is the same as CMake name of the property, so in this case compile options. The append keyword means that we are not overwriting the list of flags that have been previously added, and we are adding a new flag. You can find more about the IDF build properties, not only about the compile options, over here. In addition to adding compiler flags, we can add other compilation definitions. For example, we can add preprocessor macros. For this, we could use target compile definitions if we're adding those macros for the component, or we can use compile definition CMake property together with set source file properties if we are doing just for a single source file, or we can use IDF build property with the same name with IDF build set property if we're doing this for the entire build. And this table shows similar functions that you can use for other things. For example, for C-specific compiler flags, C++-specific compiler flags, and for the linker options. Now, for target compile options, the distinction here is that you will have to use generator expressions that depend on the language. I'm not covering this here. You can find the recipe for using target compile options with generator expressions in CMake documentation. Another common thing that sometimes we have to do is to add external libraries, meaning libraries that are not yet ESP-IDF components. And there are two cases here that I want to cover. First is when we add a CMake library that supports being added via add subdirectory command. Many CMake libraries can be added to your project using add subdirectory. And in this case, typically wrapping such a library into an IDF component is really easy. You put the library into a subdirectory of your component, either using a Git sub module or just downloading the source code. You can also download the source code during the build process. You register the component as an empty component that doesn't contain anything, and then you add that downloaded library using add subdirectory command. Sometimes you have to specify additional options. These will depend on the specific library that you're adding. In this example, I'm adding the FMT library, and FMT library has a specific option to disable the installation features. And finally, to actually attach that library to our component, I use target link libraries, linking to the component library, meaning the library of this component declared with IDF component register, the target library, the one that has been added using this add subdirectory command. For many CMake libraries, the approach will be very similar. There are other cases where it becomes a bit more complex. For example, if the library doesn't use CMake build system, or if the library doesn't support being added using add subdirectory. In this case, you typically have to use external project add command to add the external build step to your CMake application. I will not cover all the details, but there are 3 examples that you can refer to linked here, and they show how to integrate libraries, different kinds of libraries into an ESP-IDF component. Embedding data and creating file systems is another thing that IDF build system helps you with. To simply add a text file or a binary file into your application so that it can later be used in C code, you can use embed txt files or embed files keywords in IDF component register command. You can also create file systems automatically during the build process. For example, for fat file system or for littleFS file systems, there is a very similar syntax where you call a command fatfs create SPI flash image or littleFS create partition image, specifying the name of the target partition where you want to add the file, the directory which contains your source files, and a keyword saying that you want to flash those files during IDF by flash. And for NVS, there is another function that has been added to IDF somewhat recently that takes a CSV file containing all the key value pairs and a name of the NVS partition, and also that generated NVS binary can be flashed together with the application, making it pretty convenient. Doing work before or after the build is commonly necessary when we need to generate the code that is later compiled, or when we have to post-process the binaries in a certain way. Generating intermediate files and using them in later stages of the build process can be done using CMake add custom command function and add custom target. You can use add dependencies to add the dependency from your component, making sure that those steps, those custom steps, are done before building your component. And then later inside your component you can use the generated file somehow. In this example, I'm generating a certain binary based on a certain source file using a custom script, and later that binary gets compiled into the application using the target add binary data. If we want to perform post-build steps, then there is an add custom command with the post-build keyword. And this command will run whenever a certain target is built as an additional step. This can be done, for instance, when to create archives of generated binaries, or to upload the binaries somewhere And then another type is a custom command that can be run manually. And in this case, we can define those commands using add custom target. This command will not be by default executed when the build process is running, but you can invoke this command manually either as a CMake target or using IDF-PI. IDF-PI supports calling CMake targets just like this, and sometimes it can be useful to wrap a certain script. For example, if you want the users of your application or your component to be able to perform a certain step, you can wrap this step into an custom CMake target, and it will be executable through idf.py. A certain number of things in the IDF build system can be customized. For example, the name of the main component can be customized using the extra component dirs variable. There is a documentation link over here. The name of SDK config file and the place where the SDK config file is located can also be customized. This is convenient if you're treating SDK config file as a build artifact and you're not tracking it in Git. You can move it, for example, to your build directory. And the build directory itself can also be customized using the -b option of idf.py. It mirrors the -b option of CMake. So you can specify in which directory you are actually going to do the build. Combined, these two customization options give us a way to have multiple build configurations side by side in ESP-IDF. And the way to do this is to create multiple SDK config.defaults files. Now, I'm showing here an example where I have created SDK config defaults files for two different products. The differences between those products will somehow be encoded in the different settings, different kconfig option values. Those can be either standard IDF kconfig options or custom kconfig options that are specific to your product that you can define in kconfig files. For each product, we will have one build directory, build prod1 and build prod2. SDK config files for each configuration will live inside the build directories. And for this layout, you can follow the link below for an example. Now, to build one of the configurations, we can execute an idf-py command specifying the build directory and specifying the list of SDK config defaults. So first the default that is part of the application, and then the second default is specific to the product, and we specify where the SDK config file is located, and then the actual commands, in this case build/monitor. Now, in order to not have to repeat all those parameters every single time, we can create configuration files or argument files. The argument file will just contain all those arguments specific to this product. We can save this argument, for example, in the prod subdirectory, let's say prod/1. And when we call ESP-IDF, we can mention this file using this @ sign, and then the name of the file containing the argument list, in this case prod/1. This is exactly the same as just listing all the arguments contained in this file on the command line, just shorter. So now to build different configurations of different products, you can run idf-py @ sign, the name of your product, and then build/monitor. And the final thing that I want to touch on is how to share components between different projects. We talked before that at some point you will find that certain parts of your applications can be reused in other applications or for other products. And if you can no longer support multiple products just with different configurations of the same app, you may want to have multiple products inside your project. Here is an example layout of a project that you could adopt. In this case, I have multiple IDF applications, one for each product inside the project directory. And there are certain components which will be common between the applications that are located in the common components directory. There are a couple ways to add common components to those product applications. One is to specify extra component dirs variable. In this case, in project CMake list file, you can add the common components into extra component dirs, and those components will be built within your project. You can either add the whole common components directory or add specific components that you need. The second approach is the one that we do recommend right now over the extra component DIRs, and it is to add those dependencies to IDF component YAML file, same way as you would add dependencies on third-party components or other components published in the IDF component registry. In this case, we just use the name of the component and the path where it's located, and this can be a relative path. This also makes it easier to later move those components, those common components, either to a Git repository, and then you can again bring them back in using IDF component YAML, changing the path keyword to Git, or using submodules if you prefer. So these are the couple ways you can structure your projects as they grow and support more products and contain more components. With that, that's the end of my presentation, and if you have any questions, I will try to answer them.